elephantiasis. People with this disease suffer a lot. It's a disease that is very painful, and this leads to a lot of suffering and to poverty. Lymphatic filariasis affects tropical and subtropical regions of the world, such as Southeast Asia, the Pacific, Sub-Saharan Africa, and also parts of the Caribbean and South America. The main strategy against the disease is mass drug administration, which is recommended to entire populations in regions where prevalence exceeds 1% annually for at least 5 years. And ideally, we would give the drugs to everyone that needs them, but in reality, resources are limited, and we need to decide which are the areas most in need. So in this study, we had 3,000 surveys of lymphatic filariasis in Sub-Saharan Africa from 1990 to 2014. So here you can see that there are some locations with very high prevalence and some locations with very low prevalence, but we don't know anything about the areas that don't have data. So the objective is to use this information to predict a spatially continuous surface of lymphatic filariasis prevalence that can be useful to understand local prevalence and can be useful for decision making. So this is the model that we use. So here at location X, we have a survey that has N people, and out of N people, YI of them are positive. People that tested positive for the disease has a binomial distribution with parameters N, the number of people in the survey, and P, that is the prevalence of the disease or the probability of having the disease. Then in a second stage, we can say that the logit of the prevalence is equal to some covariates plus random effects. So in the covariates, we're going to put factors that we know that affect lymphatic filariasis transmission, such as precipitation, vegetation, elevation, land cover, population density. And then we're also going to include random effects to model variability that cannot be explained by the covariates. And we will put a spatial random effect and also an unstructured random effect. So when we fit the model, this is what we get. So we get a spatially continuous surface of the prevalence. Here we see that the risk is higher in the east coast of Africa and Madagascar, and also in pockets on the west, and the risk is lower in Ethiopia and in the center of Africa, in the impact of interventions. So the second example is about leptospidosis in Brazil. Leptospirosis is a disease transmitted by the urine of the rats or an environment that is contaminated by the urine of the rats. People with leptospirosis have fever, headaches, and also more severe symptoms such as pulmonary hemorrhage syndrome. Leptospirosis is an urban health problem due to the rapid and disorganized expansion of urban centers that creates ecological conditions for rat-borne transmission. And it affects vulnerable populations such as farmers and residents of urban slums in the tropics. In this study, we analyzed leptospirosis in Paula, Lima. Paula, Lima is an urban slum community in Salvador de Bahia in Brazil that hosts a densely populated community with a high annual incidence of leptospirosis. So here we see an aerial photograph of the region. So we have 4 valleys. In the bottom part of the valley, there is a lot of vegetation, and the households have very bad sanitation structures. And in the upper part of the valley, these households are close to a main road, and the sanitation conditions are better. Here we can see some photographs. We see that the households are at different elevations. There is a lot of vegetation, open sewers, accumulated trash, and people carry out risk activities such as being in contact with mud and water that could be contaminated. So our objective was to understand the spatiotemporal patterns of leptospirosis and identify targets for intervention in Paula, Lima. We recruited 2,003 subjects and followed them for a 4-year period. And each year, we administer questionnaires and GIS mapping to determine social, behavioral, and environmental risk factors. So this is the model that we fitted. Yij is equal to 1 if the person I at time j has the disease and 0 otherwise. And this can be modeled with a Bernoulli distribution with the probability of being infected. And then the log of the prevalence is equal to some covariates plus random effects. For the random effects, we use a spatiotemporal random effect where there is an occurrence on the previous time and also on a component that is temporally independent but spatially dependent at each of the times, and also a component to model susceptibility within individuals. Then for the fixed part of the model, we collected all of these variables. So these are grouped in 8 groups. Like we have demographic and social status factors, such as gender, age, being literate, health factors, such as diagnosed with dengue since last visit or vaccinated against yellow fever, occupational exposures, such as working in Paula, Lima or in garbage removal, household environment, such as elevation of the household or distance to the waste sewer or trash dump, household and work behavior, such as being in contact with flood water or sewer water near house or near job, and household and work reservoirs, such as observing rats near house or near job. So we collected all of this information, and then we followed an approach to select some of these covariates to be in the fixed part of the model. This approach is the following. So in each of the 8 groups, we selected some of the covariates. And we did that by fitting a model, a generalized additive model, using all the categorical variables, nonlinear effects of the continuous variables, and interactions between them. Then we removed covariates one by one until obtaining a model with the minimum ASC. Covariates in each of the groups. After that, we merged all the covariates selected and fitted another model using all the categorical variables, nonlinear effects of the continuous variables, and interactions between them, and explored further simplification by backward elimination until it was no longer possible to reduce the AIC. So by following this approach, we obtained a model with these covariates, and these are the results. We saw that the risk of leptospirosis was higher in year 4 compared to year 1 and was lower in year 3 compared to year 1. We also saw that risk factors were being male, being illiterate, observing rats near home, and contact with mud near home. And we also saw a nonlinear effect of age, by which the risk of leptospirosis increases until age 20, and then it's more or less constant. And this makes sense because young people have more risk activities, such as being outside, barefoot, and with contact with mud and water that could be contaminated. We also examined the residuals to identify locations where the risk was higher than predicted by the risk factors. Here, for example, we have a region that is a high-risk region in which the measured risk is consistent with prediction. And here you can see we have a lot of vegetation, open sewers, accumulated trash, and rats can be seen very easily. This is a location with high positive residual. So the risk is higher than predicted by the risk factors. And this is because we have poor household construction and there is flood risk due to poor infrastructure. And finally, these are locations with high negative residual. So the risk is lower than predicted by the risk factors. And this is because we have open sewers that in principle increase the risk, but these sewers have barriers to stop overflow. So the risk decreases. So now I'm going to talk about statistical software. So I also develop software so my methods can be widely available and provide benefits beyond my own applications. I'm the author of a spatial AP app, and this is a shiny web application for disease mapping, detection of clusters, and interactive visualization. So here the user can upload the data, can upload the map, and then by clicking some buttons, they can obtain risk estimates by fitting Bayesian models using INLA, and they can also detect clusters by using the scan statistics in SAT-SCAN. And then they can visualize the results in an interactive way using leaflet maps, tangent plots, interactive tables, and they can also generate reports with the analysis conducted. I'm also co-author of a package called EpiFlows. This is a package for risk assessment of trial-related spread of disease. So, as you know, infectious diseases may spread beyond national borders. People living in one location can go abroad and infect people abroad. And also people that come to the infectious location for holidays, for example, can get infected. And when they return to their home countries, they can infect people in their home countries. So this package implements a mathematical model to predict the number of cases that could be spread to other locations from an infectious location together with uncertainty measures. And it uses information about the number of infectious cases, population flows, lengths of stay, and incubation and infectious period distributions. So the total number of infections introduced in a location from an infectious location is equal to the exportations plus the importations, and then the uncertainty can be generated by sampling from the incubation and the infectious period distributions. So right now I'm working on statistical methods and computational tools to solve challenging problems and improve population health. I'm very interested in precision disease mapping. So as you know, disease maps are very important to understand the geographic and temporal patterns of diseases, identifying risk factors, measuring inequalities, and allocating resources. And usually, these maps are given at an aerial resolution. So here, for example, we have a map that shows malaria prevalence in Mozambique. So here we can see that in the north, in the countries in the north, the prevalence is higher than in the south. And this gives us an idea of the burden of the disease, but this is not very useful for decision making because in a given area, we only have one value and we don't know how disease risk varies within this area. So I'm working on methods to disaggregate area level data and produce high resolution estimates that allow us to identify locations of high and low risk. And this is much better for decision makers in order to allocate resources in areas of greatest need. I'm also interested in digital health surveillance systems. So as you know, surveillance systems are critical to the early detection of epidemics and to design control strategies. But traditional surveillance systems have a limitation, and is that information is delayed from the time that the person gets sick to the time that the person decides to go to the doctor, goes to the doctor, have the laboratory tests, and that information is in the system. It may take a few weeks. So this information is not useful for taking action in real time. Nowadays, we have access to other types of data. For example, digital data. We have access to social media data, where people chat about how they feel, or Google searches, where people search about treatments for their conditions. And this information is not produced for epidemiological research, but we can use it to understand disease activity levels in real time. We also have access to demographic and environmental risk factors, and there are many diseases, for example, malaria, dengue, that are affected by temperature, precipitation, humidity. So this information can also help us to forecast disease. So my objective is to develop a modeling framework that integrates multiple data sources to produce local probabilistic predictions of disease activity in real time, and also creating a dashboard that alerts public health officials when elevated disease levels are anticipated. And finally, I'm also interested in the development of interactive visualization applications for policymaking, in particular, digital web health atlases of cancer, cardiovascular or infectious diseases, and also digital health surveillance systems to monitor diseases in real time. So before finishing, I want to tell you that if you are interested in studying a PhD in statistics, KAUST offers very good fellowships that offer free tuition, monthly living allowance, free housing, and medical insurance. And here you have some links about the university, KAUST, and also information about the statistics program and the admissions website. Here, there are some references. The Spatial Health Data book, if you're interested in learning how to fit spatial models for disease mapping and also for other applications in ecology, criminology, or any other discipline that uses spatial data. Then there are several references for statistical methods and software, and also applications in health and environment. And that's it. Thank you very much.
Thank you very much, Dr. Paula, for informative and interesting presentation.
Thank you.
Thank you. Ladies and gentlemen, now let's welcome our third presenter. He is Professor Idil Oso. Little information about him. He is from National School of Applied Sciences, Qadi University, Morocco. His education, Bachelor of Science, Segora, Morocco. Master of Applied Mathematics, Qadi University, Morocco. DEA in Stochastic Modeling, Rouen University, France. PhD in Statistics, Rouen University, France. Habilitation Research in Statistics, Qadi University, Morocco. His research interests are decision theory, multivariate statistical analysis, non-parametric regression on functional data, and non-parametric models for functional data. He will deliver a presentation entitled Generalized Partially Linear Single Index Models for Functional Data. Ladies and gentlemen, please welcome Professor Idil. Professor.
Hello. Assalamualaikum.
Waalaikumsalam.
Waalaikumsalam.
How are you? You are fine?
You are fine? Yes, your voice very clear, Prof.
Alhamdulillah, okay.
Alhamdulillah, okay.
Just one.
Yeah, time's yours.
Time's yours.
Okay.
Okay.
Professor Idil,
Wait.
Professor
you can hear you.
you can take your,
Just
You can share right now, Professor.
Professor.
I cannot partage.
I'm very sorry, Professor.
I'm very sorry,
Because
because
you can
you
can share now.
You can say now.
Professor Idil,
Oui.
what
I have
happened?
I have just one problem. I cannot partage your. I can.
Cannot share, I think.
Yeah.
The operator can help to allow him.
Already.
Professor Idil, maybe better if you send your material for the computer. Yeah.
Yeah.
You PowerPoint to my WhatsApp.
Professor Idir,
Yes.
excuse me. Yes. Could you send your material? Could you send your material by WhatsApp or by Gmail? Hello, Professor Idir. Are you still there? Unfortunately, maybe there is a problem with Professor Idir connection. And then, ladies and gentlemen, while we still waiting for Mr. Idir, I think we can continue for question and answer session. Okay, ladies and gentlemen. Okay, thank you. Yeah, thank you, Professor Idir. Okay, thank you, Professor Idir.
Oui, yes. It's okay now?
It is clear now. Yeah,
it is okay. Okay.
Yeah,
It's okay.
Yes.
Okay.
Assalamu alaikum.
Waalaikumsalam warahmatullahi wabarakatuh.
First, I would like to thank the member of organizing and scientific committee for inviting me to the 4th International Conference on Statistics, Mathematics, Teaching and Research, which give me the opportunity to make address to you today. My talk has titled Generalized Partially Linear Single Indice for Functional Data. I am from Kadayad University in Morocco. For this talk, first I give you some historics and motivation. The general linear models noted by JLM are proposed first by Nelder and Widram in 1972 by the form for G of UX is it is equal beta x. This model asymmetry response come from the exponential dispersion model family, and the same authors they extend linear model to allow the relationship between the prediction and the function of mean continuous or discrete response. Strong a canonical log function. For log function, it's very interesting for us. This model encounter problem as the canonical log function is sometimes unknown. This is some first problem. For link between response and predictor can be complex, as well as plage of dimension reduction. To address this problem, several approaches has been developed in the last year. For example, Hasti and Tipshirani in 1919 proposed the generalized additive model, in which the linear predictor depends linearly on smooth of predictor variable. One of the criticism of this problem, this model, is that they not take into consideration the interaction between covariates. The paper in for the and all are the last reference dealing these two models for models GML and GM. The cycle index, when we interest model, has been employed to reduce the dimensionality of data and avoid the curse of dimensionality. Well, many to advantage of non-parametric smoothing in multivariate regression case over the last few did that see for example Lee and all on 2440. The cycle at this alpha x aggregate the influence of the observation value x in RD of explanatory variable into on one number. Like if we use the sample index to explanatory variable into one number. Alors, for example, the example of economics and this include the following. For example, a stock index, inflation index, cost of living index, and price index. This is some example of economics. Alors, furthermore, this idea has first been extended to the functional setting data by Ferrati and Vieux in 26 for functional regression problem, which led to functional sets and this regression model noted by FSIDN. Thus, the functional and this act as filter, permitting the extraction of the part of explaining the scalar response U and play an important role in such model. The predictor single model. By applying the local quasi-likelihood function and the kernel type of smoothing by approximating the function est à 0. And a general partial linear single index model was proposed by Chin Yang, Lee, and all in 2018, in which the now smooth function of single index was approximated by spleen function, then can be expressed as a linear combination of spleen based function considered as F the form. If you know the difference of the last model and the next this model, here without eta 0, and we add the function psi. Easy modified feature scoring model. However, Young and Co have studied the general linear single model by applying the causal likelihood and polynomial spleen smoothing for same models. In recent years, the analysis of functional data has made considerable progresses in imaging processing, and biomedical study, and environmental science, etc. Several research has focused their effort on studying this type of data. You and all have proposed a cycle and this partially functional linear regression model, combining the single index beta and Z has a functional. Jean-Du al. proposed the G-linear function partial linear model using a functional partial component analysis of the form, which change here on segment this for G of U of X and Z. Then the objective of not our work is to combine the model general partial linear 5 indice model and 5 indice partial functional linear model, ou combine two models and consider the flow general partial functional indice model is using B-spline expansion and the causal likelihood Q given by this formula. For any number U and V, we might be right V is graph F V minus 2 over sigma 2 VT, where V is here. Now, the objective of this paper is first to give estimator of parameters alpha and for two functions beta and eta. Then we establish their asymptotic distribution. In the end, we illustrate through some example of model and the efficient of proper estimation methodology. Now, for assumption, we present asymptotic, but to give is the first, you give estimator and asymptotic distribution. We need to some assumption to give asymptotic result. We need the some condition. This condition we have need to condition. For first condition, discrete that the second index function eta 0 can be approximated by function B-spline space with normalized basis. For the second condition, we ensure the uniqueness of the solution. For the three condition is a smooth condition on the joint and marginal density function of single index alpha x and x. The conditional 5 always to obtain the rate and trend of the dimension of the spline space relative to single size. For 6 and 7 are recurrent to covariance function between the gradient of the density of beta. To 8 condition is a smoothness condition for slope function. And the last, and for 19 and 11 are the taken R for demonstrate and give some lemmas, technical lemmas. First result, the flow theorem stated the convergence with rate of our estimator, the estimator of eta of under the assumption C1 to condition 8, we have a different the estimator and eta 0, the norm of is equal the grant of improbability. Here we have the norm 2 and the norm n, demos of n. The second theorem is under assumption C1 to 8, you have the normality of the convergence normality of beta, the second norm of beta is equal to this quantity. Now, to estimate delta, we need some result. The next theorem shows that the maximum quasi-Lyell estimator is root consistent and asymptotically normal. Alton, the convergence rate of non-parametric component eta is slow that root n before we give note that this quantity. This is for technique Lima and technique demonstration. The result is here. We have the convergence normality of alpha to alpha 0 and delta to delta 0, where D is the function suivant R and R is, and G here is Jacobian density, and here is the identity matrix. Donc, our result now, we are proved that our estimator are asymptotic normality distribution. Now, you give some, for example, of the function Z in the figure below. We illustrate for 500 resolution of a function random Z, who can have the form ici, the random of Z. The Z is a functional. Here we have data functional, is the form of Z. And we give also the observation, the almost linearity of single index here. Single index, you see here, is the alpha transposition X predicted single index as the form. And we give a function and estimate function case for n is equal 500, and then you have a slope function, and here we have a estimate loss function. It's for same function. Now you give a eta function and estimate eta function. For read, you have a eta function. Now, to finish my result, I want to give you some numeric study for eta and delta and beta. We conduct a simulation study in order to show our result efficacy. We will treat the mean case of the length function, the identity, and the logic length function. We give two functions for our numerical study. First, I calculate if the density of Y is given X and Z, as Fx is a family of exponential, canonical exponential, then the length function G is equal, expectation of this quantity is equal here. Now, for identity length function, we consider YU A of the form. The response are simulated according to the equation 5.4. XER take uniformly on interval minus 0.5 and 0.5, where area, the error, epsilon E, has a normal distribution.
Excuse me, from Idil.
We, yeah.
We still have about 10 minutes ahead. Yeah.
Okay, just I give you some one result. Now, for eta, for example, for delta, you have delta is the base SD and the meso. For n is equal to 10, and we give the same for gamma and for delta. And for conclusion, this paper, we introduced estimator of the general partially linear index models for functional data. Our estimations are obtained via the Fisher scoring adaptive equation derivative from the causal likelihood function and normalized B-spline based in their observed derivation. And then we prove the n consistently on asymptotic normality of our estimator, and therefore, and in finally, we are giving a numerical CD interval that our estimation procedure perform with in hydrodimension. Thank you for your attention.
Okay, thank you very much, Professor Idil, for interesting talk. Once again, thank you very much for all invited speakers for their informative and interesting presentation. Very well, ladies and gentlemen. Now we come to question and answer session. Please raise your hand if you have any question, or you can use chat facility. Please mention your name and state to which presenter you address your questions. Well, ladies and gentlemen, yeah, we have already some questions here in facility chat, but before we read in facility chat, maybe there is audience to give question. Okay. Okay. Yes, there are some questions here, and still there is answer for presenters from Mr. Sukarna. Yeah, Professor Benoit have give answer for him. Here there is from Hermansa. Yeah. For from Hermansa, he addressed his question to Professor Benoit. Yeah, his question about what is the difference between stepwise and lasso invariable selection. Oh, okay. All of questions for Benoit have been answered. Okay. Here there are some questions for Dr. Paula from Sri Ayu Astuti. Why did you use binomial distribution for spatiotemporal modeling of leptospirosis?
So, well, I already wrote it in the chat. It is because we have a response variable that can be equal to 1 or equal to 0. So it is equal to 1 if the person has a disease, and 0 if the person doesn't have the disease. And this is why we use a Bernoulli distribution.
Okay, thank you for Dr. Paula. Yeah, there is a question again still for Dr. Paula from Sukarna. Yeah. The questions is the life path in FE flows was very interesting. What is the difference between epiflow and Bayesian network or PET analysis?
Well, so Epiflow is just an R package that implements a mathematical and mechanistic model to predict the number of cases that could be spread to other locations from an infectious location. And it uses like equations that model this spread due to travel. So it's fitted in a different way. It doesn't have anything to do with Bayesian networks.
Question from Sri Ayu Astuti. Her question for Professor Idil. Why did you combine GPL and S, Professor
Yes.
Idil?
Yeah.
Yeah, please. Yeah, from Sri Ayu Astuti. Yeah, why did you combine GPL SEM and SEPLM using baseline?
You are used for
Hello, Professor Idil.
Yeah, we are combining the generalized partial because in our model you have two parts. The first part, if you look in the first part, when we have just general single without z. Z is a function. In our models, we suppose that the function z is a functional function. In the first, for example, in general partial linear single and this model, you have not a functional data or is real. But in our models, in the second model, when we have single and this partial functional linear models, we have linear models with functional data, and we have generalized model without functional data. If we combine two, our model, we have is a linear model with functional data, and it is a general single and this with functional data. We combine the model of Philippe and Ferrati and the model of Du Chiang in 1990. It's okay?
Okay, thank you, Professor Idil.
Using basically spleen, it's for demonstration. For demonstration to find the estimator of delta and beta and gamma, we need to use the spleen in the demonstration to give our algorithm that the estimator converge the two beta and converge to alpha and converge to delta.
Okay, thank you. Yeah, thank you for the good explanation, Professor Idil also. I have a question for Professor Benoit. Yeah. Yeah. Still, there is a question for Dr. Paula from ASWI. Yeah. Her question is, can we combine the three kinds of spatial data, area data, geostatistical data, and point data for spatial or spatial temporal modeling?
So yes, you can do that, but you need to be aware of all how the data were collected, because sometimes it will not make sense because they are collected with different procedures and they are not representing the same underlying spatial process. But if you take into account all of the biases of the data, all the resolutions of the data, and try to fit a model that accounts for all of that, you can do it.
Dr. Paula, still there is question from Doni. Yeah. I'm very interested with your experience building some application for health map data. Can we use other software application such as Quantum Gears to do this?
Yes, so I work with R and I work with Shiny to build web applications, but there are other software packages available. So one of them is QGIS, and yes, you can explore other possibilities. I don't have experience with QGIS, so I cannot explain what is available to do with it, but can choose from.
Okay, thank you. Yeah. Maybe there is question again from audience. Please raise your hand, or you can use chat facility in our virtual Zoom. Okay, I think it is clear right now. Ladies and gentlemen, now we come to the end part of the session 2. I'd like to thank so much to the all invited speakers for informative and interesting presentation. And also thanks to the participants for very active participation. Hopefully this session will be beneficial for everybody. Now I give back to the Master of Ceremony for the next agenda. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very
Good afternoon.
Waalaikumsalam warahmatullahi
much, Dr. Ruliana. And ladies and gentlemen, now we are moving to the next session, which is the token of appreciation for our distinguished speaker. So I would like to invite the head of Statistics Study Program to give the token of appreciation for our speakers. Ladies and gentlemen, please welcome Professor Muhammad Arif Tiro, PhD.
Arif.
Assalamualaikum.
Thank you very much for this time for me. Thank you, Chitra, and I would like to say that we are happy and a great honor to have you here, all the invited speakers, all the participants for this section. I think all for you have contributed important knowledge for us, and on behalf of Universitas Negeri Makassar, I would like to virtually give the certificate of appreciation to all of the invited speakers. Please kindly receive this certificate of application, and we hope we can meet again at similar activities in the future. May we stay healthy and in the protection of Allah. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Thank you. I think we return to the master of ceremony.
All right, thank you very much, Professor Arif Diro, PhD, and also thank you very much for all of our speakers today. And ladies and gentlemen, that's the end of our session today. And we would like to inform to you that tomorrow we still have the second parallel session, and also we would like to invite you to join us tomorrow at 10 October 2021. And the room will be opened at 8 a.m. in the morning. Thanks a lot for all your active participations during this sessions today. See you tomorrow. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, Paula.
Thank you all.
Thank you, everyone.
Thank you, Paula.
All right. Before we leave the room, please, we will have a presentation. So please open your video. So the committee here will take a screenshot of all of you at every page. All right. Now we will have a screenshot for the first page. All right, second page. And the third page. All right, thank you very much for your participation. And again, wassalamualaikum warahmatullahi wabarakatuh. See you tomorrow.
See you.
Waalaikumsalam warahmatullahi wabarakatuh.
See you.
Thank you.